Let's take a look at problem 8.3. So in 8.3 we have a shaft shown here. When in use, this shaft is going to experience completely reversed torsion. So this is a torsion problem. That's going to become important when we're taking a look at some of our figures and tables. It is machined. Again, another key word here is that it's machined from steel, and it gives us the hardness as 150 BHN. So Brinell hardness scale here, we're at 150. It also tells us we have a safety factor of 2. Now it wants us to estimate the value of the reverse torque that can be applied without causing eventual fatigue failure. So they give us quite a bit in this problem statement, and they also give us this diagram below here that shows all the necessary dimensions. So we can see, okay, the center diameter here is 20 millimeters, the two end diameters at 24 millimeters. On the left hand side we have a 2 millimeter radius, and on the right hand side we have a 0.8 millimeter radius. Now that we've had time to take a look at the problem statement and the given schematic, we can now write out our first page of the format for our solution, which, as we recall, as in all of our homeworks and exams, is to write out everything that we're given, simplified version of our diagram, what we're asking to solve for, and the assumptions that we're going to make. So in this problem here, first things that we know is it's a shaft and it has a known hardness. Going to experience reversed torsion, so this is going to become important here that I'm experiencing torsion. It's made of steel. It gives us our hardness as a Brinell hardness of 150, and it tells us that our safety factor is equal to 2. So we write all that information down here. If there's any units, make sure we have it in the right units. All the key material properties, loads, all of that are clearly stated here on the first page. Then we redraw out our diagram. So this is pretty close to what's given in the problem statement. I know I have my center shaft diameter here, my outer diameter is out here, my radius here, my radius here, so those are all clearly defined. Now what are they asking us to solve for in this problem? Well, they want us to estimate the value of the reverse torque that can be applied without causing eventual fatigue failure. So again, we're looking for reverse torque in this here, so we need to choose our solution based upon this here. What are our governing equations that are associated with this? The next step in this is to make the assumptions. So the one assumption that we are going to make in this problem here is that the shaft is manufactured as specified with regard to the critical shaft geometry, which again we see this critical shaft geometry up here, which is going to become important when we're taking a look at these small radiuses for our critical point later on in the problem solution. So next we'll start the analysis for our solution here. So we look through everything we had on page 1 where we know all of the given information, given schematic, and what they're looking for and the assumptions we're making. And from that we need to choose our governing equations in which to solve the problem. So one of the things that we did note in the problem statement, this was steel. So for steel, from the same table we used in the previous problem here, we have that our yield strength is equal to 0.5 times the Brinell hardness number in KSI. So that's the main difference here. Make sure if we're paying attention here, if we're in KSI, this is 0.5. If we're in PSI, this is 500. So we have to make sure we're in the right units here when we plug in these equations. Again, this is from table 8.1 in this chapter. So for our specific problem, we have a hardness value given to us as Brinell hardness is 150 KSI, so we can plug that into this equation here. So SU is equal to 0.5 times 150 KSI, which gives us SU is equal to 75 KSI. So for this problem here, we're going to convert this to MPa. How do we convert to MPa? Well, we see our scale factor here, 1 KSI is equal to 6.895 MPa. So we plug in our values here from above. So we had our SU value here of 75 KSI times the scaling factor here. So 1 KSI, there's 6.895 MPa. Multiply through, KSI cancels out. The two units cancel with each other there. We're left with MPa. So therefore, when we do this here in MPa, this is 517 MPa for SU. So the next step here is we can go to figure 8.5 and we can get this relationship here, where now we're looking for the fatigue strength for rotating and bending. So we have here Sn prime is equal to half of Su. So Sn prime is equal to 0.5 times that value we had in MPa up there above, 517 MPa, so therefore our fatigue strength for rotating and bending is given to us as Sn prime equal to 258.5 in the units of MPa. So here's figure 8.5 that we just referenced in our solution to this problem. If you take a look down here in the bottom right hand corner of figure 8.5, we can see that equation we were talking about right here. Sn prime is equal to 0.5 SU. So this is the relationship we're using here in order to solve for that. For the next part of our solution, we need to calculate the endurance limit, or S sub n. So we can go back again to table 8.1 and we can get this equation here. So we have S sub n defined by our Sn prime, Cl, Cg, Cs, Ct, and Cr. Where for each of these variable names we have our Cl is our load factor, Cg is our gradient factor, Cs is our surface factor, Ct is our temperature factor, and Cr is our reliability factor. And if we take a look at table 8.1 and figure 8.13, we can go through and get values for all these for our specific problem. So going back up to our load factor, our C sub L, we have this is equal to 0.58. And we can get this from table 8.1 for torsion. Now our C sub G, our gradient factor, is equal to 0.9. If we go back to that table 8.1 for torsion, look that up as well. Now for this one here, we have to pay attention. What is our diameter? There's two different values based upon the diameter. So our diameter falls between 10 millimeters and 50 millimeters. So that's why we choose our 0.9 for this one here. Then we can take a look at our temperature factor. So our temperature factor is given by 1, a value of 1 if we go back to table 8.1 and take a look at our torsion value there. And our reliability factor from table 8.1 is also given as 1 as well. So from these values here, we can then plug back into the equation that we got up here for S sub n, or our endurance limit, from table 8.1. So now let's go to table 8.1 from our textbook. Generalized fatigue strength factors for ductile materials, or SN curves here. So our governing equation that we showed in the previous page for our solution is based off the torsional load here, where S sub n is equal to S prime n, C sub L, C sub G, C sub S, C sub T, C sub R. So we rewrite this over here, the same equation that we saw previously in our solution. And now what we need to do is go through and define all of these new variables here. So we'll start with our C sub L. Our C sub L is our load factor. Now this is for torsion, as stated in our problem statement here. So our C sub L for torsion gives us a value of 0.58. So C sub L is equal to 0.58. Then we take a look at C sub G, our gradient factor, where now we need to determine where does our diameter fall for this here. Is it less than 0.4 or 10 millimeters? No, but it is between 10 millimeters and 50 millimeters. So therefore our gradient factor C sub G is 0.9. So C sub G is equal to 0.9 over here. Then we can go to our next factor here, our C sub S, our surface factor, which now, in order to do that, we're going to jump to figure 8.13. So we'll put that on hold for a minute, and we'll come back to that afterwards, and I'll show you where we can pull our C sub S for our surface factor from figure 8.13. But for now, let's go to the next variable here, our C sub T. Our C sub T is our temperature factor, which if we look this up under torsion is 1. Our C sub T is equal to C sub R is equal to 1. And then each of these values along with our C sub S will then be plugged back into this governing equation up here with the numeric values that we find. So now let's jump to figure 8.13 in our textbook in order to solve for our C sub S value here. So now let's go to figure 8.13 in our textbook in order to get our C sub S value. So 8.13 is reduction in endurance limit owing to surface finish, which again is our C sub S that we're looking for. Steel parts, which applies for us here, we're dealing with steel. That is surface factor versus tensile strength for various surface conditions. So that lets us know that we're going to need to know our tensile strength when we come in here. So we've already solved for this based off the information in our problem statement here, that S sub U is equal to our ultimate strength is equal to 75 KSI, and it's machined steel that we're dealing with here. So if we come down here to our two axes, we can see down the bottom here is our SU value in KSI. Here's our C sub S, our surface factor up here. So what we can do is we go over, we have a value of 75 KSI, so we come down to this bottom axis here, our x-axis. There's 80, there's 60, the center of it would be 70. Split that again, there's our 75, so we can draw a line straight up. And we go all the way up until we hit the curve for machined, because that's what we're dealing with here is machined steel. So we go all the way up to that curve here, and we can see it's just below 0.8. So we have a value for C sub S of 0.78. So now that we have a value for our C sub S, or our surface factor of 0.78 from figure 8.13, based upon our ultimate strength here of 75 KSI, we can plug that back in here for our C sub S value here into the equation for our endurance limit from table 8.1. So that's what we do down here. There's our C sub S value, 0.78 down here, plug in all our values. We have our S sub N prime value here of 258.5 and units of MPa that we solved for earlier in this problem. We have our C sub L from table 8.1 at 0.58. We have our C sub G, or gradient factor, of 0.9 from table 8.1 for torsion again there. Then we have the C sub S value. We have our C sub T of 1 from table 8.1, and our C sub R equal to C sub T equal to 1 there. We plug these values in, plug into our calculator, we end up with our S sub N, or our endurance limit, equal to 105.3 MPa. So for the next portion of our problem, the first thing we're going to need to do is find our critical point. So for our particular problem here, our critical point is at our radius of 0.8 millimeters. And we'll take a look at this in our given diagram, and when we get down to our figure for our geometry and figure 4.35 in a little bit more detail. And for figure 4.35, we're going to need to have our ratios between our critical radius, which was defined as 0.8 millimeters in our problem statement, our given geometry, and our schematic. Our inner shaft diameter of 20 millimeters. We divide those and we get 0.04. We also need a ratio of our big diameter over our little diameter for our shaft, which in our particular case is 24 millimeters over 20 millimeters, or a value of 1.12. And again, we'll go into this in a little bit more detail as it relates to the geometry when we take a look at our figures 4.35 and our figure 8.23 down below. So first thing we want to do is take a look at figure 4.35, which we're going to get our geometric factor of K sub T. So now let's take a look at figure 4.35 from our textbook. So we're going to take a look at diagram for C, which is torsion, which is what we're dealing with specifically in our problem. So we can see up here we have our chart for C here. Here's our diagram here in general form, where our capital D is this outer diameter here. Lowercase d is the inner diameter of the shaft here, and our r is this inner radius here, where we're dealing with our critical inner radius, which would be on the right side of ours there, which gives us a value of 0.8 millimeters. Now if we take a look at this diagram here, the bottom axis is our r over d, our lowercase r for our critical radius there, divided by our lowercase d, or the inner shaft diameter there. And our y-axis over here is our K sub t value that we're going to solve for. But then there's three different curves. So each of these curves are defined by our value for big D over little d, or our big diameter over our inner diameter there. And now what we want to do is figure out what are our values for r over d and d over d for this problem here. So we go back up here. Let's take a look for our value on our x-axis here. Our critical radius here is 0.8 millimeters. Our inner diameter is 20 millimeters for our specific problem, which gives us a value of 0.04. And then our big D over little d, choose which curve we're on, is 24 divided by 20, which gives us a value of 1.2. So that lets us know that we're dealing with the center curve here, with a value of 1.2, and our r over d is giving us a value of 0.04. So here's a value of 0.05. We're halfway there, so 0.04 is right here like this. So next we can do is draw a line right up and figure out our K sub t value. So now we draw on our lines here. So if we go over to the x-axis value for r over d of 0.04, we can draw that line straight up till where it intersects with our 1.2 curve here. We draw our line straight across to get our k sub t value, and what we see now is we have a k sub t value of 1.65. So if we go to figure 8.23, we can see that we have preceding situation is common dealt with by using a notch sensitivity factor Q. So in order to find Q, we can utilize equation 8.2, but we can also take a look at figure 8.24, in which we can use the graph there in order to get a value for our Q, or our notch sensitivity factor. So now we'll take a look at figure 8.24 in our textbook, and what we see here is we have a plot over here that we're going to utilize in order to find our value for Q, or our notch sensitivity value here. So what we can see here is we have our bottom axis over here, our x-axis of our notch radius. For our critical notch radius, pay attention, we have inches and millimeters. Choose the correct one. We're dealing with millimeters for ours. And we have our Q value over here on the y-axis, and we have all these different curves for various hardness values, but also for axial and bending and torsion. So make sure we use the values on the right here for torsion for our specific problem here, rather than bending and axial over here on the left. And again, we'll go down to millimeters, so we have 0.8. So we want to go to 0.8 millimeters here. Then we'll go up until we hit our curve for our Bernal hardness number, come across over to the left here for our Q value. So the closest thing to our Bernal hardness number is 160, even though we're at 150. So it's a little bit less than that there. We come across, we see we have a value for Q of 0.74. So now we can come back over here for our solution. We've gone through and looked at figures 8.23 and 8.24. And from figure 8.24, we were able to get a value for 0.74 for our Q, or our notch sensitivity factor. So then we can go to equation 8.2, which we saw at the bottom of figure 8.23. So equation 8.2 on page 232 of our textbooks gives us this value here. Our K sub F, or our fatigue stress concentration factor, is equal to 1 plus our K sub T value, or geometric factor, minus 1 times our Q, which we just solved for above from that chart from 8.24. So now we know our K sub T for our geometric factor. We know our Q for our notch sensitivity factor. We can take those two values, plug them into equation 8.2, and that's exactly what we do here to get our K sub F, which again is our fatigue stress concentration factor, equal to 1 plus 0.65 minus 1 times 0.74, which gives us a final value of K sub F is equal to 1.48.